All right, now let's start to set up our sum. We're adding up all these rectangles and we're doing it in general. So each rectangle has the same base. We've already established that the base is 4 over n. Right, so remember yesterday when we did our problems, we knew we were going to have the same base for each rectangle. So same thing here. We have 4 over n times the area plus 4 over n times the area of the next rectangle, and so on until we get to the last one. So in order to get the height for each rectangle, remember we just plugged in an x value. So for this first one, we talked about how our first x value, x sub 1, is 1 plus 4n. We would plug that into our function. So we'd have 1 plus 4n, 4 over n, squared. To simplify it down here for right now, we're just going to write it as f of x sub 1. Right? We put x sub 1 into that function. That's going to give us the height of that rectangle. So we have the base times the height. So that's our first one. First base times the first height. Then our next one, same thing. Same base times our height is going to be f of x sub 2. Then we're going to have 4 over n times f of x sub 3. And then our last one is going to be 4 over n times f of x sub k. Okay, now we need to take this and put it in sigma notation. So we're going to find the sum from k equals 1 to the nth term. Right, we're doing this in general, so we could set it up at the end of this if we wanted to try it for 10 rectangles or 100 or 1,000. We could plug any of those numbers in for n. So each one of these has the same base. So when we're doing our sum, we're going to have that base times, it's just f of x sub whatever term we're on. So this is going to be f of x sub k. All right, that represents any number. Now, for this one, we already talked about what x sub k is. So the whole point of kind of setting this up here was to get this value, because we have to take that value and substitute it into our function. We're just doing it in general. So we're going to look at the sum from k equals 1 to n of 4 over n times f of x sub k. So we're actually taking x sub k, which is this whole value, and putting it into our function. Remember, our function is x squared. So this whole thing is going into that function. So we're going to take 1 plus k times 4 over n squared. Right, so that's our function with our kth term. So we're just putting that general term in for x. So we're squaring it. Now is where we're going to have a little bit of fun with some algebra. We need to go ahead and kind of multiply this all out. So we have the sum from k equals 1 to n. And we have the 4 over n out in front. And we need to multiply this part out. So like using FOIL, we're going to have 1 times 1, so we get 1. Then 4k over n, or 4 over n times k, times 1, and we're going to add another one of those. So we're going to end up with 8 over n times k, plus, if we do 4 over n times k, that times 4 over n times k, we get 16 over n squared, k squared. All right, so all we did was take this and multiply it out using FOIL. Now, we can go ahead and distribute the 4 over n. So we have the sum still from k equals 1 to n of 4 over n plus 32 over n squared times k plus 64 over n cubed times k squared. Well, this brings us back to what we did on Friday. Before we kind of move on, I need to remind you that this right here, this n, is a constant. All right, n is a constant. That's just a number. It depends on what we decide it to be. So this is a constant, this is a constant, and this is a constant, right? K is our variable. So each one of those things is a constant. Now, those rules that we talked about on Friday with sums come into play here. We can split this up. Remember, with addition, we can break it into smaller pieces. So that's what we're going to do here. We're going to take the sum from k equals 1 to n of 4 over n plus this 32 over n squared. I'm going to bring that out in front of the next one. Because remember, with constants, we can bring that out in front of the sum, in front of the sigma, because it's one of those properties of sums. Plus 64 over n cubed. Again, that's a constant. We can bring that out in front. Times the sum of k squared. Well, we talked about this. What happens if you take the sum of a constant? Again, don't let that n fool you. This is still a constant. So if you take the sum of a constant, remember there was a formula for that. We take this times this, right? We take the constant times the number of terms. So that's going to be 4 over n times n. Remember we did like the sum of 5 from k equals 1 to 6. All we had to do is take 5 times 6. Same thing here. It looks more complicated, but same basic idea. All right, next one, the 32 over n squared, that's the constant. It stays out in front. Times the sum of k. This is one of the ones that we talked about and had a formula that you need to remember. That's going to be n times n plus 1 all over 2 plus 64 over n cubed, again, constant stays out in front, times the sum of k squared, another formula that we had, n times n plus 1 times 2n plus 1 all over 6. All right, a little algebra here, a little distributing, a little combining like terms, some canceling out of things. This first one, we have the n's are going to cancel out, so we're just left with 4. Here, 32 over the 2, that's going to simplify to 16 over 1. This n cancels out with one of these, so we're left with the 16 n plus 1 on top over n. I'm actually going to distribute that 16 to both of those. So we get 16n plus 16 all over n. Over here, the n cubed, get rid of one of those and cancel it with that one. Our 64 over 6. The 64, take a 2 out of that. We have 32 with 3 left on the bottom. So what we need to do on this one, a little bit more, we're going to distribute here. We get 2n squared plus n plus 2n, so 3n, plus 1. So that becomes 2n squared plus 3n plus 1 on the top, but we also have that times 32. So I'm going to go ahead and distribute that 32 to each one of those. So we have 64n squared plus 96n plus 32 all over 3n squared. Now, to go ahead and simplify a little bit further, 4 is good how it is, but here 16n plus 16 over n, we can basically divide both of these terms by n. So if we take 16n divided by n, we're just left with 16. If we take 16 over n, let's go ahead. All right, let's go ahead. I'm sorry. Let's write this out. For the first time, I'll kind of show you what I'm talking about a little bit better. We can split this up as 16n over n plus 16 over n for this part. Plus, do the same thing over here. Split each one of these. So we get 64n squared over 3n squared plus 96n over 3n squared plus 32 over 3n squared. Now, you may not need to write all of this out every time, but just to kind of let you visualize and see what I did, we can go ahead and simplify that. Here, the n's cancel out. Here, n squareds cancel out. One of the n's with this one, and we can simplify the 96 over 3. So we end up getting 32. So we're left with 4 plus 16 plus 16 over n plus 64 over 3 plus 32 over n plus 32 over 3n squared. All right, algebra fun almost done. We can go ahead and combine like terms. So we have constants here. Well, we have numbers without any n's in them. They're all technically constants. And we have 4 plus 16 plus 64 thirds. So if we add those up, we get 124 thirds. Plus we have the 16 over n plus 32 over n. We get 48 over n. And then a 32 over 3n squared. So remember, we did this in general terms. So now, if we wanted to find the area under the curve using 10 rectangles, we could just put 10 in for n. If we wanted to find the area under the curve using 20 rectangles, which we did yesterday, we could put 20 in for n. We can keep going, 100, 1,000, whatever we wanted. Now, we talked about how by making more rectangles, we're getting a more accurate area under that curve. Well, here's where the calculus comes in. We did a bunch of algebra right here. Now it's calculus time. If we want this n to keep getting larger and larger, right, the larger it gets, the more accurate it gets, we think about what kind of thing that we talked about earlier this year. As n gets bigger and bigger, we're talking about a limit. If we take the limit as n approaches infinity, as the number of rectangles gets larger and larger, of this expression right here, that's going to give us the exact area under that curve. So the limit of that is going to give us the exact area. And this goes back to some old stuff. If we have a limit of a constant, that's just going to be the constant. If we have a limit of a number over n, as n approaches infinity, remember this number, as the bottom gets bigger and bigger, the actual value of the whole fraction gets closer and closer to 0. Same thing if there's an n to a power on the bottom. So the exact area under that curve is 124 divided by 3. And that comes out to approximately 41.33 square units. All right, so let's kind of take a look back at what we did here to find the exact area. For the exact area, we ended up taking the limit as n approaches infinity of the sum from k equals 1 to n of delta x times f of x sub k. All right, so this is our formula to find the exact area under the curve. And we're going to make some connections. I've been promising you that we'll make some connections between this and integrals in the next few days.